So in the interest of time, I'll introduce our speaker today, and she really needs no introduction. She's been a Berkeley person for a long time, professor of electrical engineering in the EECS department. Avideh Zakhor has her degrees from MIT and Caltech. She's got a list of awards and accomplishments longer than both my arms, so I'm going to move on straight away to introduce her. She's our speaker today. Her topic is fast automated 3D modeling of building interiors. Avideh.
Thank you. Can everybody hear me fine? Yes. Okay, great. So the outline of my talk today is roughly as follows. I'm going to talk about some related projects, then switch to indoor modeling, which is the main topic of this course, of this talk. Localization, model construction. I'll talk a little bit about image-based rendering and some future work. Before I get started, maybe it helps to show the video.
Researchers at UC Berkeley have developed a laser backpack that can scan its surroundings and then create an instant 3D model. It's technology that can make video games more realistic and buildings more energy efficient. Richard Hart reports on the drive to discover a new model of everything around us.
Here's a model of 2 floors of Corey Hall.
This is the first model of an existing building made without human intervention. It is the work of a Cal Berkeley team led by Professor Avideh Zakhor. Grad student Nicholas Corso dons a backpack brimming with lasers and cameras. As he hikes the hall, the lasers scan floor to ceiling and the cameras capture a panorama.
The idea is you wear a backpack, you walk inside the building, you're done, push a button, and out comes this model.
A model textured with the photographs. This team is also behind technology that creates 3D views of major cities on Google Earth. Why not fly into these buildings too? Well, the outdoor version relies on GPS. You can't rely on GPS indoors. So Professor Zakhor's imaging lab combined a new breed of miniature laser with an inertial management unit like the one that guides missiles. That IMU localizes the backpack, lasers generate the geometry, and cameras generate the texture map. All 3 are fused for precise navigation.
Once it's turned on, there are 4 cameras snapping pictures simultaneously. One looks left, one looks right, this one looks at the floor, and this one takes a picture of the ceiling. At the same time as this laser looks left, this laser looks right, this one looks at the floor, and this one looks at the ceiling. And up front, the most sophisticated analog component ever devised.
With this, you can walk stairways and caves and places a robot just cannot roll.
One day you'll have a little pack of sensors in your belt, and as you walk inside buildings, you collect data. So every location, indoor and outdoor in the universe, will eventually be mapped, and we'll have it all online. So without ever going anywhere, you can see what everybody's interior looks like.
With the next step in mapping, Richard Hart, ABC 7 News.
All right. So there were few inaccurate things in the video, and as I go along the talk, I'll try to clarify them. But for the most part, they give you an idea of what the project is about. So before I get to talk about indoor modeling, I want to just spend 1 minute on outdoor modeling, because there's a lot of similarities between the two, and there's some major differences. So between 2000 and 2005, here at UC Berkeley, my group was working on fast modeling of urban environments, like cities. So the idea was to equip a truck with laser scanners and cameras and other sensors and drive by in cities under normal traffic conditions, and using that build what we call a ground-based model or a terrestrial model, and then fly overhead to collect laser scans for the rooftops, and also fly overhead to take pictures from the rooftops, and then make using those to make airborne model. And then merge the airborne and the ground-based model in order to register and fuse them in order to come up with a complete 3D city model. So this was a picture of Google Earth, just entirely 2D of downtown Berkeley. You could probably recognize the BART station here and the tall Powerball building there. And after we put our 3D exterior model on top of it, it would look something like this. So this is before and after. Similarly, that's another viewpoint before and after. So clearly 3D makes a big difference when it comes to outdoor modeling. Now this is already being deployed by Google Earth logistic trucks. They're all over California, US, and the world collecting laser scans to build models of cities that you can look online. The topic of today's talk, though, is mostly indoor modeling. So let me start by stating what our goals are. We want to make, in a fast and automated way, we want to make a 3D model of building interiors so that you can eventually do virtual fly-throughs and walkthroughs inside buildings. And eventually the goal is, just like the video said, from the exterior, if you're driving in a city, you can seamlessly go inside a building and have the same virtual experience that you had outside as you would have inside. And the applications are numerous. I'll talk a little bit more at the end, but basically training, simulation, games, entertainment, law enforcement, modeling public places like hospitals, schools, for firefighting and first responding applications, all of those. So here's a simple description of the concept of operation. So you equip the backpack with a bunch of sensors, like the guy talked about, cameras, laser scanners, IMUs, walk around the building, acquire the data, and then process the data offline, but without human intervention, to come up with a photorealistic 3D model. And the first question that you'll be asking is, why do you want to wear a backpack? Why not have a robot with wheels or pushcarts? Well, the answer is we want to be able to do staircases and uneven surfaces, places where robots and pushcarts and things with wheels will have a hard time going. And automatically, because we now choose a backpack system, that puts a constraint on the weight and power of how many things, how many sensors, and how heavy this thing can be, both power requirements and weight requirements. As it turns out, to solve this problem, the biggest challenge is what's called localization, which means figuring out where the backpack is at every point in time and what angle it's looking at. So in technical jargon term, we want to know its X, Y, Z location and orientation, yaw, pitch, and roll. And we want to know that as a function of time. And this is a hard problem for indoor because there's no GPS inside the buildings to tell us X, Y, Z. GPS only works outside. Even for our outdoor projects, even though we didn't use GPS, we used aerial imagery to localize. That aerial imagery is also not available inside, so we're out of luck there. And the reason this problem is hard is that if we had the luxury of using carts with wheels or robots with wheels, then we could have used not only visual wheel odometry, but also we only had 3 degrees of freedom of pose to recover, just X, Y, and yaw in one plane, because when you have things on wheels, they don't tip over. So there's really just 3 degrees of freedom to recover for your localization. However, a human operator really has 6 degrees of freedom pose in a sense that as we move, X, Y, and yaw change, but also pitch and roll and Z changes. So even though you think your height doesn't go up and down as you walk, it really does. And your hips move, and that results in pitch and roll. So we need to recover all these 6 degrees of freedoms. So here's a picture of backpack. This time Matt Kahlberg is carrying it. And here are the various sensors. The L stands for laser. The C stands for camera. The orientation measurement unit, InterSense, which is a tiny thing, is here. And we also have a ground truth device from Honeywell. It's called, it's an inertial measurement unit, HG9900, which we primarily used for ground truthing and developing our algorithms. It will not be in the eventual backpack system if this ever becomes, for example, commercialized. So this is by far our heaviest component, and it has a mini computer associated with it, and it requires you to stop a whole minute after 2 minutes of walking. It has a lot of things associated with it that are not necessarily desirable or easy to use, but we have it here for now just so that we can develop our algorithms and have a ground truth. So here's a list of components. I won't go into it again. The ground truth piece and the one component I forgot to mention is the battery. So we have an external 170 watt-hour battery pack with regulators. So before I go into talking about localization, here's a simple concept of operation. So we have, as the person is walking parallel to the wall, let's say there's a right vertical laser scanner that hits the wall, and as the person moves, this scanner scans the wall top to down. So if only you localize the backpack, in other words, would know the exact position and orientation of this laser scanner, you could stack up these vertical scans just the right way such that the resulting point cloud will give you the 3D geometry of the facade you're looking at. So that's why we need localization. We need localization so that we can stack up these vertical scans in the correct manner. And because all these scanners are mounted on the backpack in a rigid way, they don't move, localizing the backpack is the same as localizing the laser scanner and localizing every other component that's on the backpack. So really, recovering X, Y, Z, yaw, pitch, roll for the backpack is the same as recovering it for every component on it. Okay? So, so this 4 steps just about summarizes what goes on. You estimate, you localize, estimate position and orientation at every point in time, build the point cloud, then you tessellate this, and then you texture map it. So let me spend a few minutes to talk about localization. At the heart of our localization, we use laser scanners to primarily in order to localize the backpack. And at the heart of the algorithms that we use is iterative closest point scan matching. This was invented in the 90s at the GM Research Lab. And the basic idea is if you have 2 scans, that's shown here, scan 1 and scan 2, by minimizing an objective function, you can find the rotation R and the translation T between these 2 things. It works well if the scans are more or less in the same plane, which in our case, they're not really because of the pitch and roll of the human operator. It works better when they're more or less pre-aligned, and it also works very well if you have an environment with rich 3-dimensional geometric features. So how is it that this can help us localize the backpack? So this is a top view so the horizontal laser scanner here, looking at 2 walls, and we're looking from the top. And on the right, what I'm showing is the laser scan plot. So as I collect the first scan, the next scan, by matching these scans together, we can determine X, Y, and yaw using this scan matching ICP algorithm. I can repeat that same thing. So what I just showed you was the top view, which is here. So by matching a horizontal laser scanner, successive scans of a horizontal laser scanner, I can deduce X, Y, and yaw. Now, this picture is a side view. So if I have a vertical scanner that's shown here that scans the ceiling and the floor, by matching successive scans here, I can recover X, Z, and pitch. And similarly, this is another side view. I have another vertical scanner that scans like this. By matching successive scans of this, I can estimate Y, Z, and roll. So just if you look at me, the yaw scanner is horizontal like this. The pitch scanner is vertical like this. And the roll scanner is also vertical like this. So by doing these 3, by mounting these 3 scanners orthogonal to each other in 3-dimensional space, we can get X, Y, Z, and yaw, pitch, roll. And in fact, that's the basis of our simplest localization algorithm. It's called 3 times ICP because we do 3 times the scan matching. 1 for the yaw scanner, 1 for the roll scanner, and 1 for the pitch scanner. So the yaw scanner gives us TX, TY, and yaw. Vertical roll scanner gives us TY, TZ, roll. And the pitch scanner gives us TX, TZ, pitch. And some of these things are redundant, but we just concatenate these and you got your 6 degrees of freedom. That's the simplest way of doing it. It turns out this algorithm is too naive and it needs to be modified and improved. So the next simplest thing to do is say, well, I have an instance orientation measurement unit, which I showed you it's only this big and doesn't take too much space or power. And I can use the pitch and roll estimate from that rather than using the scan matching along the pitch and roll directions. And it turns out this performs better. And the reason we don't want to use the yaw values from this device is that it uses the Earth's magnetic field in order to determine yaw. And in indoor environments, there's a lot of steel cabinets and other things that distort Earth's magnetic field. And it turns out the yaw values that it spits out is completely garbage. So you're better off just even throwing it away. So this algorithm, it runs ICP twice, and then it uses the inner sense orientation measurement unit in order to give us the pitch and roll. And you get the answers. And finally, the third algorithm that we tried, which even does better than the first 2, is to take advantage of situations in which the floor is planar. I know I started this talk by saying that we want to go into staircases on even surfaces where you're walking is not necessarily planar, but it could be that 70% of your walking area is planar and 30% is staircases. For the planar area, it turns out you can get improved performance if you fit a straight line to the laser scan that hits the plane, compute the slope of it, get m, and then plug m here in order to compute the pitch. And once you know the pitch, you can compute the absolute z height of the scanner. And it turns out this method of calculating z, the height, is extremely accurate. It's much more accurate than the other two schemes that I talked about earlier. And of course, you can mix and match, and this whole scheme results in an algorithm which I call 1 times ICP plus IMU plus planar localization, in a sense that we only using this scheme, it turns out you only need to run ICP once, and that's for the x, y, and yaw computation. The z comes from this computation, the pitch comes from here, and the roll could essentially come from the orientation measurement unit. Okay, so I already described a few ways of localizing, and each of these localization methods gives us this transformation t that tells you that the change from time 1 to time 2. So you can build a graph where the nodes are absolute localization values at each time instant, and this t12 gives you the transformation from time 1 to time 2, t23 from time 2 to time 3. Now, if you concatenate these things and do what I just said, these calculations, and start at position 0, 0, go along the hallway and come back, and you concatenate these vectors, even though you physically return to the same position, concatenating these does not let you get back to the same position. Why? Because the errors accumulate. There's drift, right? These calculations are not perfect. And this is called dead reckoning. And that's why the title of this slide is Dead Reckoning Has Unbounded Error. And in fact, if I was going to plot this in an XYZ plane, I start at location 0, 0. The green path that I get here goes all the way up in the sky. It is telling me the operator flew in the air 6 meters, which we already knew he didn't, right? So what we need to do is something called loop closure. And what that means is once we get to the same position as we were, let's say we started at position 1, we went to position 5, and 5 and 1 are the same, we need to detect we came back to the same position and close the loop. So the idea is that if you revisit the same location, and if you can detect that you're revisiting the same location, and I'm going to tell you how you do that detection in just a second, then you can compute in this slide, you can compute the transformation that takes you from 5 to 1 by doing scan matching, for example, between 5 and 1, compute T51, and then you can solve an optimization problem in order to enforce consistency, i.e. saying that this is the transformation that relates the position at time 5 to the position at time 1. Okay? And the way you enforce that consistency, as I said, is by solving an optimization problem, is to also have, besides computing the transformation between each two time instants, you want to have an estimate of confidence in that transformation, or an error bound in that transformation, which we denote by sigma. So in this diagram here, not only do we estimate t, but we also estimate sigma. That's the measure of uncertainty that we have about t. And in this diagram here is the size of these circles. So for example, in this path that we traverse. So if we go on this path, when the size of this ellipsoid is big, it means there's a lot of uncertainty between the one position and the next position. And when they're small, it means there's little uncertainty. So by minimizing this optimization problem, you're essentially distributing this uncertainty that you have between any two nodes in an optimal way. Think of it as mass and springs. You let these positions wiggle in the optimal way so that you can enforce the fact that what the path that you traversed was actually a loop, a closed loop of some kind. Okay? So in this diagram, if I start from time 1, go position 1 to 2 to 3, 4, 5, 6, 7, 8, 9, 10, we want to, for example, detect that 10 and 1 are the same location or very close to each other. They're not the same, but close. And 4 and 9 are the same or very close locations to each other. So how do we do that? Well, before explaining how we do that loop closure, let me just summarize the approach. So the first step, we compute these transformations using any of the algorithms I talked about and their associated covariance. And then we, for each loop closure event, we close the loop and do this global optimization to get final estimates. So the question is, how do we detect loop closures? And the way we do that is we use our camera. This is somewhat of a known problem in computer vision. There was a technique called FabMap introduced by Cummins and Newman in 2008. We can use images, and if you have a series of images and you start at position A, you walk around, drive around, come back to the same, or approximately the same position, it can detect that you're about the same location. So in this set of pictures, this is third floor of Corey Hall. We walked around, came back, and this image is entirely different from this, but it detected that we're in the same location. So I won't go into the details of FabMap, but basically it generates a ranked order list of candidate image pairs for loop closures. And it uses SIFT features and Bayesian inference, a maximum likelihood framework to do so. So if you run 100 trials of FabMap, let's say in an image database for let's say, third floor of Corey Hall, it comes up with image pairs that it thinks are close to each other with high probability. So in this example, you can say that it thinks of the 100 trials, it thinks that pair 85/1 image have a very high probability, and this one has this probability, etc. Now it turns out in this example we got lucky, and the highest two probabilities are indeed true loop closures. But many times it's not, so you can't just pick the top two. But if you look at the probability distribution function of the ratio of the features in each pair, you can see that the distribution here is quite different from the distribution there. And we can use this differential in order to detect which image pair it spits is correct and which ones is incorrect. I won't go into the details of how we do all of these things, only to say that this approach works pretty well. It's so far worked on all the data sets that we've collected so far. Okay, so moving on, let's go back to our premise where we started. We want to be able to do complicated environments like staircases. So these plots here shows us 4 data sets for February of 2010 that we collected. And for example, in this data set, we start at location 0, 0, go all the way down the hallway, come back, go upstairs, go down the hallway upstairs, come back and down the stairs. And these red dots show the loop closures. And the red is the ground truth as defined by that expensive sensor that I just talked about, and the blue is our recovered path. And as you can see, we recovered the path pretty nicely. And this is not the entire localization, because localization is not just X, Y, Z. It's also orientation, but I'm not showing you orientation in this plot. So using the ground truth, we can also figure out the error in orientation, the error in position. But kind of a nice metric is shown in this table. For example, in this data set 4, we walked 142 meters about, and average position error is 43 centimeters. That means on average, each position is about 40 centimeters or so off. Okay, so once you localize, i.e. compute X, Y, Z, and yaw pitch roll of the backpack, you can then build the point cloud, and that's shown here. So this uses the 1 times ICP plus IMU plus planar approximation to give us the estimated path, which is red, and the black is the ground truth path, and this is the point cloud that we get by stacking the vertical scans. So notice that each device is serving multiple purposes. The laser scanners were used both for localization and for giving us geometry. And the camera is going to be used both for texture mapping the final model and localizing us. It already helps us to do the loop closure, and you'll see in a second, it also helps us refine the localization. So each sensor serves dual purposes. Okay, so once you have the point cloud, you can make a colored point cloud, 3D colored point cloud. And you can go inside the tunnel and look at the 3D colored point cloud. Now we have to figure out a way to actually make surfaces out of it. And one simple way is to say, okay, the vertical scans that we get come in a specific order, and each one has order. We know which point came before another point. So this is not a really hard, unordered point cloud triangulation problem, which takes a long time and is a difficult problem. We can just simply, using this partial order, triangulate. And this method we just call triangulation. Alternatively, you could say, well, most indoor structures have planar or surfaces or well-known geometries. Why don't we just fit planes into them? And we've done both. So here's an example of a piecewise planar approximation of the 4th floor of Corey Hall. This is looking inside the hall, and as you can see, the artifact that you introduced by doing so is that there was a box here that was extruding from the wall, but because we did a planar approximation to the whole wall, it got flattened, which is not good. This is an example of a model you get with scanline triangulation. It's not as clean as the planar model, and there's ways to kind of improve or fix that. This is the same triangulated model looking from inside. Again, there's some mismatches and some wiggly things going on. So for one thing, when you look at these models, you can see that there's misalignment between the images. So even though we localized our system with lasers and the OMU, they didn't localize us to pixel level accuracy. So if you want to have pixel level accuracy, you better use your cameras to achieve better localization or get finer localization than what you had before. So to that end, we modified that Toro optimization that we did earlier. Remember we talked about loop closure by optimizing these things. So these little nodes show the laser scan matches, the transformations that we got using laser scan matches, right? On top of that, we can use image matching in order to get additional transformations like T12 prime, T23 prime, etc. between these nodes in order to enforce that pixel level accuracy in localization that we need. And we do that solving another optimization problem. We're basically saying that we need to have consistency across the images. And by doing so, if this is our before image with all these misalignments here, here, and here, we can get something really aligned and nice that's shown up there. Or we can get something misaligned that's shown here, and processing it, we can get something really aligned like it's shown there. You can also remove these intensity differences here by doing gain adjustment and also blending. And the example of blending is shown here. These lines here disappear if you blend the images, and that's a well-known technique in graphics. Okay, so then you can, these are some examples of two-floor models. This might be and this is an example of a T-shaped model. This might be a good point for me to show you a 3D demo of the model that's shown here. You can interact with it. So I can spin it around and turn it over this way. Okay, and zoom in and zoom out. Oops. Get closer, and then rotate it. And if I was really good at playing video games, which I am not, my son is quite a bit better than me. We can make ourselves walk through the hallway. I have to first zoom out. Ooh, wow, okay. Spinning out of control. Okay, zoom out, rotate, and perhaps I can zoom in and go inside the hall. Ooh. Okay, I'm not going to test myself in this under these conditions with the laptop buttons and everything. What we've done is we put the texture of the interior also in the exterior, so I don't have to go inside the hallway. But if you do go inside the hallway, you can pretend that you're. Let me try one more time. You know what? This model is slightly different from the one I practiced with. I used to be able to enter here, but it's not very easy to do that now. Maybe I have to enter the other side. Yeah, that might be. Oh, okay, better. Okay, now zoom. Ooh, oh, I went the wrong way. Okay, enough of this. You know, when I was a grad student, this just reminds me, I can't resist not saying that there's a 3D flight simulator that I think I didn't play enough with that. If I had, I would have done better. Okay, all right, so these models, by the way, are sitting on our webpage. You can download it and look at it if you're interested in. So what are some interesting things we can do with these models? One thing we can do is, rather than looking at these models explicitly and spin them around and do video game type things with it, we can do what's called image-based rendering in graphics. And what that means, the image-based rendering can be summarized as follows. So suppose I have a large collection of images from a space. And I want to put an imaginary eye in that space and I want to quickly compose the right images from that database to give a view from the imaginary point to the user. And as the user changes his or her viewpoint, that view gets updated. So you retrieve the right images, compose them together, mosaic them together, and show them to the user. So in this application, you're also getting the feeling that you're in a virtual environment, but you avoid building the actual explicit 3D model. Now, why is it that I want to do image-based rendering? Well, remember, we localized our backpack. That means we localized our cameras. That means we know the pose of every camera image in our backpack, X, Y, Z, yaw, pitch, roll. So knowing that, you can easily compose together and mosaic together images for any arbitrary view you're looking, and even do image interpolation, in order to retrieve the right view at the right time. Okay? And so you can imagine the user navigating using a keyboard and a mouse to rotate, translate, and switch between ceiling, floor, etc. And let me try to show you a video of that Tim Liu generated. So here it's an imaginary eye floating around 4th floor of Corey Hall. This is not necessarily the path we walk. And we're composing images on the fly depending upon where the user is looking at. And this was done essentially over a summer project, so there's many improvements that could be done to it. I'm hoping it gets to the end where suddenly we can even look up to the ceiling and look at the floor and view things that we didn't even directly capture. Yeah, now we're looking at, I forgot, is this the floor or ceiling? Floor, ceiling, right. You can see the lights and change the view, and you can see the floor, etc. So here's kind of one interesting thing you can do with these models. Oh, it's not really with the models. Information that we retrieve during the model generation, we can exploit it to do image-based rendering, for example. Yeah. What about if we keep the questions at the end? The next thing we can do is indoor augmented reality. So you all know what augmented reality is. You point your cell phone in the street to some building, and all this metadata about information about that building shows up on your viewfinder, right? So indoors, you don't have GPS, so it's not very easy to do indoor augmented reality. Also, however, we're in the process of generating the indoor model. Remember, we recovered the geotagged images. We covered the localization for all the images we captured during our walk. So using the same technique, you can have a cell phone indoors. For example, you're in the shopping center, you point your cell phone to something. It can localize you. It can, for example, by matching the image that you take with your cell phone with the image database, and by knowing the absolute pose of all the images in the database, it can figure out where you are in that gigantic 3D model, and it can spit out the right information on your cell phone viewfinder if that's what you're looking for. Or if you're lost in the mall and you want to go from point A to point B, it can help you figure out how to get from point A to point B, because by taking a picture and matching it against the images that we just collected in our indoor modeling, you can localize yourself. So this is has tremendous applications or implications in things like location-based advertising. So as an example, we've actually done some of this initially in the outdoor shopping center, in the Emeryville shopping center. On the right-hand side is the image database we collected, and on the left is the cell phone picture we took, and it correctly retrieved the right image. And this is our performance. 90% of the time, or so 95% of the time, the top image which we retrieve is the correct image. And sometimes it retrieves the incorrect image because the angle of the cell phone picture is too much of an acute angle. So if you do that, you can also do what's called tag transfer. So this is a query image and the cell phone, and this is a database image. So you can transfer the tags from the database image into the query image. We've also done it for indoors. So we took the same models that we have for Corey Hall. We actually took a cell phone and used it to see, can we localize ourselves? So we did it against the 2nd floor and the 5th floor of Corey Hall. Not sure why there's only 2 curves but 3 labels here, but for the 2nd floor of Corey Hall, we can get 80% recovery, correct recovery of localizing the user accurately. And the reason 2nd floor does so much better than 5th floor is because 5th floor is just a collection of offices with numbers on them. There's no distinguishing features, whereas 2nd floor is, I don't know, has trophies and pictures and other nice things that can help you localize. A few words about future work. We want to improve the visual appearance of the models. The gain compensation is not exactly right. Improved localization is always our goal. Things always work out better if you have better, lower error. We want to make models that are watertight. In other words, the floor and the ceiling touch each other and they're 90 degrees and impose a priori constraints, more a priori constraints than we've done so far in terms of the final model, how they should look like. Simplifying the models is no good if the resulting model of the fourth floor of Quarry Hall is a gigabyte worth of information. Nobody can put it on their desktop or laptop, let alone their cell phone. Rendering and interactivity is useful. That's why the image-based rendering was a nice standalone project. We want to also characterize the accuracy in a more systematic way. Let me end by talking about a few applications of this technology. In architecture, if you're remodeling your house, you can use this to reverse engineer floor plans. Currently, for a 1,700 square foot house like mine, it takes a week of laser scan measurements in order to build the model. You can imagine if you wear this backpack and walked around, you could be done data collecting in 20 minutes and build the model in 2 hours rather than a week. Plant and factory facilities, keeping track of their assets, the location of their equipment, condition of the equipment, can have applications there. Public areas such as schools and hospitals, it'll be good to have a map, a 3D model of those for cases of emergency, for firefighting, law enforcement, first responders, etc. Public places like airports, bus stations, and transportation facilities. You enter Grand Central Station, tell me how I get from here to my train to Boston. Those are places, by the way, that have a lot of stairs, a lot of escalators. It's not easy to push carts. A backpack system is extremely useful, and it's good to have 3D maps of them rather than the 2D. Other public places like music halls, stadiums, theaters, etc. Gaming and entertainment. You can imagine that you can personalize the video game that your son plays by putting Berkeley High School 3D model when he plays it and Beverly Hills High School when my niece in LA plays it. That's personalized to each one of them separately. And obviously underground mines and tunnels. These are places, again, where you can't push a cart or a wheel thing, and it's important to have a backpack to get a complete 3D models of those. I'm going to stop now for any questions. Yeah.
Okay, please use the microphones for your questions.
Hi, very nice work. I'm just curious about the types of lasers that you use to scan the walls and if there are any limitations as to scattering or absorbance of the materials involved.
Yes, if you looked at the third floor, we have two kinds of laser scanners. One of them is slightly more high-end than the other one. The low-end one, when it hits shiny floors that are also happen to be dark, it doesn't give us any return. So if you were really careful in the two-story model that I showed, the third floor of Quarry Hall has no floors. And for that reason alone, we're switching to the more high-end scanner. We've tested it in the high-end scanner. We can get better returns. So that's a very good point.
Just to follow up on that, how robust are the algorithms to kind of, I guess, sensor quality? One of the things I'm wondering is, for example, there's the Microsoft Kinect sensor that came out that gives you these registered 3D image data. Would you be able to adapt the algorithms to something like that, for example?
Yeah. So people have applied the Kinect system to indoor modeling, but just of a room. The range of Kinect is very limited. It's only 4 meters or so, and its accuracy is not so high. But if you just wanted to model like your dormitory room or your office, it can be done, and there's already YouTube demos of that on the web that you can use. But it uses a different technology. It uses a projector camera technology, right? And so because of that, it's inherently limited. And also in its size, it's bigger than the laser scanners that we use, and it's also in range. The range it can capture is smaller. But for some applications, small rooms, it's applicable.
I'm wondering how much are you limited by computing power, or is the problem more software oriented?
Who asked that question? Me. Oh, okay. How much? Sorry.
I'm wondering to what degree is the computers you're using limiting how quickly and accurately you could build the 3D models, or is it more a software?
It's more algorithms. We're not compute limited. Most of the algorithms go through fast enough. The localization is a big challenge, and there's errors, uncertainties, and really misregistration, I would call it. We're now just calibrating the various sensors you have on the backpack is a big problem. Calibrating the OMUs with the lasers, with the cameras, and if you have, even though I said they're in a rigid body, right? And we used a CAD model. We gave it to the machine shop, and they built it for us. But that's not enough accuracy. For example, the registration between camera and laser, that's only within few millimeters. You really need to have these things calibrated a different method so that they're pixel accurate. So that's kind of what we're spending a lot of our energy on these days.
Do you think you need better accelerometers and gyroscopes?
Oh, we could definitely benefit from a better gyroscopes and accelerometers. For example, the ground truth that we have, that results in the best models, but it's not practical. First of all, it costs us $250,000. Second of all, for every 2 minutes you walk, you have to freeze for a whole minute for it to correct itself. And third of all, it's very heavy. Fourth of all, it consumes a lot of power. It's just the list goes on and on and on. So yes, I mean, that's an extreme example. If you just had that, you could make nice money. But even then, you still have to do the loop closure. When we close the loop, sometimes actually we've reached a point that sometimes our algorithms, after closing the loop, performs better than that $250,000 kind of piece of equipment, right? So definitely better sensors will do. I would say that the gyroscopes are one of few things that if you pay more money, there's a chance to get better answers out of it. Not always, but sometimes. But definitely with the less expensive units will definitely generate lower quality measurements. So the question is, how do you fuse these measurements that each have their own uncertainty and noise and error in order to come up with something more accurate?
Thank you.
Yeah, I've seen similar here. So I've seen similar two works. One is under the balloon, and they were like scanning. The other one was
in the air. In
the air, right? And the other one was like your system. One was carrying all the sensor, and the other person is carrying the batteries because they are really heavy. And the both methods were using the shape from structure from motion technique, using the images. And I wonder why you first register all the localization problem by only using the 3 laser points rather than using the image sequences.
Yeah, we have tried to use. You can use cameras for localization, structure from motion, as you just mentioned. It has a lot of problems. Recovering dense depth using those is not easy. You can recover depth. For example, the same way as lasers need rich 3D geometric features, cameras need rich 2D features for all of these methods to work. So if you're walking in an area with a blank wall, which is a lot of buildings in a lot of places, which doesn't have any pictures on it, those methods fail very quickly. We have also tried to just use images, and it doesn't come even close to the accuracy that you get with laser scanners.
Thank you.
But as you can see, images were used to refine the answers that laser scans. I mean, that's another problem with structure from motion. You're solving a nonlinear optimization problem, and it's highly dependent on the initial condition. So essentially, we are using lasers to give you the initial condition for that, and then refine that in order to gain pixel accuracy. Right?
I wonder, piggybacking on the same question here, I wonder up to what point, so I've seen research in the structure from motion using only a single camera to do dense reconstruction, Andrew Davidson's lab, for example. I wonder, seeing that research is coming to fruition nowadays and they're able to do real-time reconstruction using, I guess it's parallel architectures. I mean,
you mean the North Carolina group with Polyphys and Michelle?
Yes, I believe so. So my question is, up to what point do you want to keep using? I mean, probably all these cameras are necessary, but up to what point do you want to keep using the laser rangefinders, or change and start using them as ground truth, seeing that all these efforts might be able to?
Yeah, I've seen that work. I don't think that work can generalize to arbitrary environments. I'm still skeptical. It works okay for outdoor because it's at a distance and the field of view is large and there's features that you can match. I think for indoors, I'm a little bit more skeptical. And I also don't think I think that the laser technology is becoming cheaper. And I think a lot of the ill-conditioned vision problems can very nicely become better conditioned with simple sensors like orientation measurement unit or a laser scanner. For example, we can miniaturize the laser scanner to be this small on a chip, and that way it's a lot more attractive than a camera. So yeah, I mean, it is possible to do it with camera only. I have seen models of it, but I still think that it's also very easy to come up with situations where it just completely fails. If you have lack of visual features, it just won't work.
Thanks.
Thank you very much, Professor Zakhor.